Okay, today we're going to have a look at proof by logical equivalence. So this is one of the more simplest methods of proof. And to prove that a statement is logically equivalent, that is, P implies Q and Q implies P, is to separately prove that both P implies Q and Q implies P are true. Now, I'm sure there are other ways of proving this. You probably could prove some of these by induction, but for now we're going to prove by logical equivalence. So with proving by logical equivalence, we've always got two cases, so kind of like part 1 and part 2. So example 1, we've got n is a positive integer, prove that n plus 9 is odd, if and only. That is another way of saying that double implication there, if and only. In fact, a lot of people call this the if and only symbol. So P, if and only Q, n minus 8 is even. So we're going to, first of all, we might call it part 1. Let's go assume n plus 9 is odd. So that would mean that n plus 9 is equal to 2k plus 1. And we're going to try and prove that n minus 8 is even. So we've got n plus 9 is equal to 2k plus 1 for some integer k. So for some k belonging to the integers. Now we want to try and prove that n minus 8 is even. Let's have a look at n minus 8. We've got n minus 8. Well, n minus 8 we could say is n. Now, minus 8 is the same as saying plus 9 minus 17. That's because 9 minus 17 is minus 8. But we know already from our assumption that n plus 9 is 2k plus 1. So this is n plus 9 minus 17, which is 2k minus 16, which is even. So therefore, n minus 8 is even. Now part 2, we're going to go back the other way. So we're going to assume k minus 8 is even. Or n minus 8 is even. So that would tell us that n minus 8 is equal to, we might say, 2k again. So for some integer k. So n minus 8, let's figure out, we're going to prove that n plus 9 is odd. So n plus 9, we could say that it's equal to n minus 8 plus 17, because 17 minus 8 is 9. But n minus 8 is 2k. So this is 2k plus 17, and 2k plus 17 could be expressed as 2k plus 16 plus 1, which could be expressed as 2k plus 8 plus 1, which is odd. So therefore, therefore n plus 9 even, if and only n minus 8. I think that's an odd there, sorry. Odd. Even only n minus 8 is even. Okay. Prove that a 3-digit number is divisible by 3 if and only the sum of its digits is divisible by 3. So again, we're proving by logical equivalence. We're going to prove that one implies the other, and then the other implies the first thing. So prove that if a 3-digit number is divisible by 3, if and only the sum of its digits is divisible by 3. Right. Let's have a look at this 3-digit number. We might call it 100A plus 10B plus C. Because if you multiply any number by an integer A times by 100, you get a 3-digit number plus a 2-digit number plus a 1-digit number, and that altogether will give a 3-digit number, and that we could express this, and this expression here would be able to give us any 3-digit number. Now, if that number is divisible by 3, we could say this is equal to 3k. But we could say that this is the same as 99a plus 9b plus a plus b plus c equals 3k. And we're trying to prove that the sum of its 3 digits is divisible by 3. So here we've got our 3 digits here, a, b, and c, because if you multiply 100 by 9, you get 900, so that first digit is going to be 9. If you multiply 10 by 2, your second digit is 2, because 10 by 2 is 20. The weird balloons. And if you multiply c by anything, well, you're going to get the same thing. So let's rearrange for a plus b plus c. It's going to be 3k minus 99a minus 9b. But 99 and 9 are both divisible by 3. So this is 3k minus 11a minus 3b. Not 11, it's 33, sorry. And that's divisible by 3. Now we've got to say if the sum of the 3 digits is divisible by 3, then the number is divisible by 3. So we're assuming that a plus b plus c is equal to 3k. So that's how we're going to go back the other way. So we're saying the sum of its 3 digits is divisible by k. But we've already said that this number is equal to 100a plus 10b plus c. We could, if we wanted to, split this up into 99a plus 9b plus a plus b plus c. And we've just said that a plus b plus c is 3k. And we can take out a factor of 3, so 33a plus 3b plus k, which is divisible by 3. Awesome, and we're done. Okay, and we might want to conclude and say, therefore, the statement is true. By logical equivalence. Awesome, a nice and easy one. Proof by logical equivalence. Thank you.